Hello, my name is Oujin Mikajiri, and I'm from Glen Eagle Secondary School in Coquitlam, BC, Canada. And the title of my work is Degradation of Bio-Based Polycarbonates: Speed, Pathways, and Persistent Challenges. Now I'm gonna talk a little bit about my research background. First of all, the the first time when I became interested in plastic pollution problem is when I saw a news that of a sea turtle eating a plastic bag in the ocean, misunderstanding that it was it was jellyfish, which is their prey, and the sea turtle choked themselves. Right? Um, and I want you to look at the figure 2 now, the total volume of all plastic ever produced. It says that 8.3 billion tons of plastic has been produced to date, and as of 2015, approximately 6.3 billion tons of plastic waste had been generated. Unfortunately, only 9% of it was properly recycled, and 79%, which is the majority of it, was went to become landfills, or it was just like released in the natural environment, which is not quite good. Now, how long does plastic take to decompose? I want you to look at the figure 3. Um, Even this little piece, tiny piece of cigarette can take 5 years to be decomposed. And plastic bag can take 20 years. Um, I'm sure that a lot of people use this daily, but each of the plastic bags that people use can take 20 years to be decomposed. That's quite a long period of time. And plastic straw is even longer, 10 times longer. It takes 200 years. And plastic bottle, diaper, toothbrush, plastic container, they are all daily used products. And surprisingly, they all take over 400 years to be decomposed. Now, so what is a good solution for this problem? So one is called bio-based polycarbonates, which are polymers that are made out of bio-based materials. The feature of them is that they they can degrade in a relatively short period of time compared to the plastics that we use right now. However, there's some questions that remain. First, one, how long does bio-based polycarbonates take to degrade? Two, what conditions are required for efficient degradation? Three, what combinations may be needed for synthesis? And four, existing challenges that remain unaddressed. Here's my methodology. First, I did a research on Google Scholar using this keyword string, and I identified 160 papers in total. Next, I scanned title, abstract, and conclusion of each of the papers, and I decided if I keep one or not based on the criteria here. So basically, if a paper discusses about both synthesis and degradation pathways, I keep it. Otherwise, I don't. And then I ended up identifying 6 papers in total, and now I started gathering information about synthesis and degradation of corresponding polymer. All right, here are the 6 papers that I used. And in my research, I was mainly focused on 5 different types of bio-based polycarbonates. 1, PIC, polyisosorbate carbonate. 2, PMC, polylimonene carbonate. 3. ICCPC, isosorbide-based polycarbonate. 4. Spirocyclic acidyl structures. And 5. BISCC, bicyclic carbonate. Here's my finding. Um, I found that there's quite a wide range of degradation periods among bio-based polycarbonates, and I would like to share some of the interesting ones with you. First of all, PLMC. Surprisingly, there's no observable reaction happened, which was quite interesting to me because um, initially I thought all types of bio-based polycarbonates are capable of degradation since they are all made out of bio-based materials. But apparently my assumption was wrong. And next good example is PIC. It shows how modification can affect degradation period. First of all, when pure PIC is decomposed, it takes just about 24 hours to complete its degradation. However, when it's mixed with acetyl groups, some of the polymer remain undegraded after 24 hours, which means it becomes more resistant. On the other hand, when it's mixed with hydrophilic groups, which means more like water-loving, then it completes its degradation just within 9 hours. That's pretty impressive. And the last example that I want to share with you is BISCC. It's because it has the fastest degradation time with less than 30 minutes at room temperature. That's very incredible. Alright, this is the table of conditions needed for efficient degradation. The one that's really interesting here is spirocyclic acidyl structure, since it kind of requires two different steps for fast and efficient degradation, unlike the others. So first of all, spirocyclic acidyl structures has to be deprotected by a strong acid, which is shown here. Initial one pH value is less than or equal to 4. And after it is deprotected, then it undergoes ammonolysis reaction, which means it is decomposed by ammonia. It is also shown here that the final pH value is greater than or equal to 11, which is very basic. And and it's also interesting that spirocyclic acidyl structure, it only requires room temperature. Unlike the others, for example, PLMC is around 60 degrees Celsius. ICCPC is even higher than 90 degrees Celsius. Alright, here are the combinations that is needed for synthesis. It shows that people literally use anything to make bio-based polycarbonates. For example, PLMC is made out of limonene oxide, which is from orange oil. And let me see. Both PIC and ICCPC is made from sugar cane. That is also very interesting. BICC use carbon dioxide. Here are the existing challenges. So, first of all, PLMC, as I said, it has very slow degradation period. It goes really slow degradation, and that kind of has to be modified. And Also, specifically for PMC, orange is very seasonal, which means the source is very limited of and it's not like you can produce orange, you know, for the entire year. Second, oh, here I want to talk about ICCPC. It is often mixed with BPAPC, which is the current plastic that we use to be more like durable or to to have more like stronger structure. But when that happens, then it really ruins the point of being biodegradable since BPAPC takes so long, like it literally takes so long to be decomposed. Finally, spiral cyclic acetal structure. As I said, it requires two steps for fast and efficient degradation, and also the conditions are pretty different from each other. Right? One is very acidic, another one is very basic. So that's a bit of a challenge. Here's my conclusion. So I believe that the ideal alternatives are those that are designed for quick and efficient degradation without damaging the environment. For example, BICC is good that because it holds the fastest degradation time with less than 30 minutes at room temperature. Another good example is PIC, since its degradation product can be used as fertilizer. All right. So finally, although they have some challenges remaining, but I believe that there is a potential for a future or for a true closed loop that is essential for us to build a sustainable future. Thank you.